When last we met, sperm were digging their way through the jelly coat of a sea urchin egg. Sperm have bindins at this point at the very front of their acrosomal processes. There are bindin receptors on the egg waiting to greet these bindins. And when that happens, the species specificity is checked. Species specificity had been originally checked a little bit by the jelly coat, but it's not a very precise job done. And now a more specific species specificity check occurs, and this blocks cross-species fertilization if the bindins and bindin receptors don't meet. So I just want to point out that here's the sperm, here's this acrosomal process, here these are photographs, go with my cartoons. The receptors are too small, the bindins are too small to be seen at this magnification. Those are called cortical granules. Okay, so we've got this impending meeting between the vitellin layer's bindin receptor and the bindin on the sperm. And then we're going to fade out. And we're going to jump ahead because now that event, which is kind of murky in our understanding, has allowed one of the sperm to continue on, and when that happens, the sperm and the egg have proteins that fit together. So here's the vitellin layer. This is happening. The vitellin layer has been dug through the plasma membrane of the egg. Here's the plasma membrane of the sperm. They have proteins that interact. This is the fusion, protein-mediated fusion between sperm and egg membrane. Sperm and egg fuse. What happens? Well, there's a interaction. I'm going to draw a greater magnification here. This interaction somehow led to an influx of sodium into the cell. And that influx of sodium into the cell changed, it's just the membrane potential. In other words, it depolarized the cell. And by depolarizing the cell, you'll notice these proteins have changed shape. They no longer look like question marks. They're all folded over. They can no longer bind. So even if the second sperm gets so far as to get through this vitellin layer interaction between bindin and bindin receptor, even if it comes through and its proteins are made available to the egg membrane proteins, well, they have a different shape now. So that membrane fusion can't happen.
What I've just described is the fast block to polyspermy.
I've also described the beginning of the slow block to polyspermy, because both of those start with that depolarization event caused by the opening of sodium channels, which was caused by the membrane fusion between egg and sperm membrane proteins. Okay. Here's our egg membrane. Sodium has entered the cell because of that fusion. Sodium comes in. Now what happens? Well, calcium voltage-gated channels open, and calcium comes screaming in. And calcium, of course, is a signal molecule. So, what is the signal? Well, the signal, it turns out, first off, this whole process spreads in this great wave of activity, this great wave of calcium entry. So here you notice that it's just hit here. Just this is where the sperm must have entered. And then it begins to spread. This is an egg cell. The dye is making the calcium glow. This is not like luciferase, mind you. This is actually the molecule calcium causing glowing wherever it's found. And you see now that it's spread, it's no longer coming in here. Now the calcium is spread over here, and then it's spread over there, and then it's spread all the way to the back end. So it's a wave of calcium movement across the surface of the membrane. What happens when that calcium enters the cell? Well, when the calcium enters the cell, it tells the cortical granules to exocytose. Remember these critters? Remember that they looked kind of like that? Well, these cortical granules now exocytose. Let's draw the exocytosis of cortical granules. Here's the egg membrane. Here's a cortical granule releasing its content into the space between the egg membrane and the vitelline layer. So that was the vitelline layer. That was the plasma membrane of the egg. What's coming out of here? Well, one of the things coming out of here are enzymes. Does that look like an enzyme? That cut all of the links that exist that anchor the vitelline layer to the plasma membrane. So the enzyme is coming from the cortical granule to break those links. There's also a bunch of stuff. Mucopolysaccharides, big long polymers, you don't have to know any details about them, are present in the cortical granule. Now they've been exocytosed, but that's not enough to create osmotic potential drops out here that are necessary to attract water into here. So not only is that sent out, but also the enzymes that eat those polymers, turning them into monomers and therefore creating lots and lots of osmotic potential, because this, say, 500 monomer long thing cut into 500 monomers now has 500 times as much influence on water entry into here. The osmotic potential is a unit by unit basis, and this is just one unit. All of these monomers are also one unit. What else? There are also components that will be added to this vitelline layer to change its chemical makeup that came out of here. And these will help turn the vitelline layer into the fertilization envelope. Water is going to come in, and that's going to push the fertilization envelope away from the plasma membrane. And what we're going to end up with is something you saw in lab. You're going to see the egg plasma membrane surrounded by a fertilization envelope, and all the poor little spermies, no chance they're going to get in. So what it's accomplished here is a block to polyspermy. Only one sperm can fertilize the egg if that egg is to survive and become a zygote. There was the slow block and there was the fast block. Both started out by sodium entry. Sodium entry changing the shape of the proteins on the membrane that comprises the fast block. Sodium entry causing calcium channels to open, and that wave of depolarization leading to a wave of calcium entry, leading to a wave of the exocytosis of cortical granules, leads to the formation of the fertilization envelope.